Welcome to BKW Physics. I'm Mr. McConnelly, and we're going to do some magnetism today. Now, even since elementary school, I'm sure magnets have been interesting to you because they're kind of amazing. You have a north-south magnet, and it's just two look like pieces of metal, and they are magically attracted to one another. You can hold a magnet underneath the table and move another magnet on top of the table. They're just fun. And magnetism is a physics topic, and we're going to start. Well, let me back up. One example of magnetism that most people don't realize has anything to do with magnetism is the aurora borealis, the northern lights. And if you've ever seen the northern lights, you look at the northern sky and you see green and reds that seem to shift around in the night sky. Now there was a lot of, as you know, in history, there's been a lot of people that have come up with reasons or theories that they thought the northern lights were there. This is long before the science could back it up. And they thought it was maybe reflections from schools of fish, because a lot of times they would see it over the ocean, and they thought maybe there's large schools of fish, and it's reflecting up into the sky, because it does dance around. And so they tried to come up with these theories on what the northern lights might be. Well, what it actually is solar wind is blowing high-energy particles towards the Earth. When those high-energy particles cross through the Earth's magnetic field, because remember, around the Earth, you have a north and a south on the Earth, and there's a magnetic field that surrounds the Earth. So as these high-energy particles pass through that magnetic field, that causes the electrons to change energy levels, and then as they do that, you see that change as visible light. So you're actually seeing those electrons jumping levels, and then you're seeing this visible light. And the reason it dances around is because you got, the high energy particles are coming through all different times and different locations, and you see this light. So it's kind of interesting, and most people don't know it has anything to do with magnetism. So, magnetism. Let's back up to the basics. How does magnetism work? If you have a chunk of material and magnetic material, what you'll notice is that in a magnetic piece of material, there are these ferromagnetic pieces. And these ferromagnetic pieces, if the thing is magnetic, they need to be pointing kind of all in the same direction. Now, backing up to your earth science days, the mid-Atlantic ridge, in the middle of the ocean, you got North America and Europe over here, and you have the mid-Atlantic ridge, which you remember is the boundary between plates, and it's separating, and so the magma is coming up at the mid-Atlantic ridge, and as that magma comes up, there's something interesting that has to do with magnetism. You may recall that the ferromagnetic pieces in the rock, as it cools, are all pointing one direction. But as you go further from the mid-Atlantic ridge, you will find that the ferromagnetic pieces are kind of drawn like this. So this is one time period. This is another time period because it's split and separated. The ferromagnetic pieces are pointing the other way. This indicates that the Earth's magnetic field actually used to point the other way. The north was south and the south was north. That's really interesting in and of itself. But what's happening here is because when this magma comes out, the Earth's magnetic field aligns the ferromagnetic pieces so that they all point in one direction, basically. And then as the magma cools, they're trapped like that. Those pieces are all trapped in the same direction, encased in rock. And so you can see these ferromagnetic pieces. Well, back to this. What does a chunk of material look like that's not magnetized? In other words, it doesn't have a north and a south. Well, it kind of look like this. You have ferromagnetic pieces that were kind of, I'm trying to draw this random. I don't know if that's really random, but the ferromagnetic pieces will all kind of randomly point all different directions. And so the net effect is this doesn't really have magnetic poles. So what is the idea of a pole? Well, if we take a bar magnet, something that you might find in lab, a piece of metal, and it's labeled north and south, these are the poles out here. And the poles are the location where the magnetism is most concentrated, it's the strongest. Now, when you have a magnet and you have poles, there has to be a magnetic field between the poles. And what happens is the magnetic field, a lot like an electric field from our previous chapter, is represented with arrows. These arrows representing the magnetic field always point, or they start in the north and they point towards the south. They go north to south. Okay? And that's just always the way we draw them. Now, if you drew a bunch of them, you'd also notice this. That, I'll just draw one arcing in this way, one arcing in this way. See how they all seem to congregate around the north and the south? In other words, the magnetic field lines are closer together at the north and the south, at the poles. And so what you can say, just like with electric fields, is since the lines are closely congregated here, and that's called the flux density, how densely packed the magnetic field lines are, since they're more densely packed, the magnetism is stronger. If you check the magnetism in this area, it is magnetic, but it's not as strong as it is when you get near the poles. And you know that if you've played with magnets, you know that the poles are the strongest location. All right. Now, what if we were to take a compass? You know, a compass, you lay a compass in your hand, and the compass, that's north. It'll tell you which direction north is. Well, what is a compass? Have you ever thought that through in your mind? A compass is simply a magnet that is free to spin on a pivot point. So, if you took a magnet, if this marker represents a magnet, and you put it on a little balancing point here so this thing could spin in any direction, it would spin so that it aligned itself with the magnetic field of the Earth. So, if it's telling me that that way is north, which end of the marker is the north end of the marker? Think carefully on this. Most of you got it. This end over here is the north end. In other words, the blue end of the marker is the south end, because the south must be attracted to the north pole of the Earth. Get that? So, if we were to place I'll draw it kind of huge. If we were to place a compass right there, okay? I'll erase that line for a second, because I just laid that compass down. That compass will definitely align the needle like this. Which way is which? Okay? So compasses point towards the, they always tell you where the north is. So the compass will point like this, won't it? Yeah. It'll say that's the north. Everyone can probably agree on that if you think about it for a second. But what most people get a little confused about is if it's pointing north, then this little arrow, which is actually a magnet, this end is the south pole, and this end is the north pole. Because the north has to be attracted to the south, and the south has to be attracted to the north. That makes sense? Okay, I don't know if you've ever thought compasses through that carefully, but that's how they work. So, if you stop back next time, you will see we will do some left-hand rules of magnetism for today.